My name is Zoe Steinkamp. If you don't feel like asking questions in this room, which by the way, this room is really friendly, like don't be afraid to grab the mic afterwards. You're welcome to add me on LinkedIn and message me there. I swear I'm very friendly there as well. So the agenda today. So we're going to go over really quick why a time series database is important, especially when you're dealing with time series data and analysis tools. Some tools to know that we're going to be going over in some of the slides. What is Apache Parquet and Apache Arrow? Apache Arrow examples, leveraging Panda for analytics, which will basically be mostly going over joins and stuff in Pandas, and some examples, including autocorrelation, anomaly detection, and I have a Jupyter Notebook for forecasting, but we're not going to go over it here. And all of these are going to have a bunch of QR codes, a bunch of resources for you. So if you feel like, it's the last talk of the day and your brain's starting to shut down a little, it's okay. We've got resources you can look at later on. So first things first, some audience questions. How many here have worked with time series data? Okay, most of the room. How many have worked with a time series database for that data? A few of the room, a little less. Not too shocking, plenty of people put their time series data in many different formats. So, why a time series database is important. So really quick, just to make sure everyone's on the same page here, time series data most commonly is going to be metrics. That's something like the temperature value is 76 at 5 p.m. today. That's a metric. They're pretty much regularly over time. They're constantly happening. The temperature is constantly a thing for the most part. Events are things that are irregular. That can be something like a button clicking on a website. That's something that's very irregular. You don't know when the button's going to be clicked. Could be at 5 p.m. today, could be at 5 a.m. in the morning. Traces are complete events or requests. This is normally very common in server monitoring infrastructure. An event is like a trace. A trace is an event where it's many metadatas included in it. It's something like you click on the button and many things are activated from that button. And so that's normally where you can see things like slowdowns and such. You can see like your authentication is taking 400 milliseconds versus loading of your website because you have 100 million images is taking multiple minutes. Those kind of times. So when it comes to a database, these are 4 different examples here. You've got your relational, which is pretty common. Most people here should be familiar with relational DB. It's the most common DB that you would use for most of your most common data, things like records, stuff that you want to hold on to, as we say long term. You've got your document database. That's things like, images, stuff that changes more regularly, those kind of good things. Document DBs also tend to be what we call NoSQL. That just means that they are not relational. And then you have your search, which also, the reason I want to point out also document and search is that these are also commonly used to store time series data depending on the way that it looks and what you're using it for. And then a time series database is just a little bit more niche in that category in that it's really specific for time series data, which means that if you tried to store something without a timestamp in InfluxDB, unlike Mongo, we would reject that data. That's not something that we're in the mood to store for you. That's not what we do. We're really good for time-stamped metrics data, which mainly comes from things like IoT devices, analytics, cloud-native infrastructure monitoring, all that good stuff. And this is a typical architecture and deployment. And I know this says Influx on it, but this is pretty much for all time series databases. This is very common. This is how it looks. We all take data sources from all types of devices, as I've already mentioned. We do the data collection, which I'll mention briefly, a few of these options. And then we do data storage and transformation, which is pretty straightforward. It's a database, it stores data. Who would have thought? And then finally, data visualization and analysis, which we'll also be getting into. So some tools to be aware of. So Telegraph is a tool that I really like to highlight, and every single tool I'm going to talk about here is all open source, just be aware. This is an open source agent for collecting metrics. It's driven by our community, which is about 600 plus contributors, give or take a day. And it's simple to configure and extremely flexible. And here are some examples of the categories of Telegraph plugins. There are over 400 input, output, and manipulating aggregators. And so this is just some of the ways that you can get some of these data types into not only InfluxDB, but other time series databases. We have connectors for Mongo, for example. We have connectors for many, many other databases because it's open source. So people just add whatever they would like to have and it works. So yeah, these are just a few examples here. These are the most popular to say the least. SQL aggregate functions. So these we're not going to go into too much. You'll see a few of these in the code examples. But I just want to highlight these because they are very useful, especially when dealing with time series analysis. The general aggregate functions are definitely like the bread and butter. Everybody's using these, especially me. Everyone should recognize count right off the bat. Some of these statistical aggregate functions, I'm going to be fully clear, I have not used all of these. If you asked me to name them all, I'm not sure I could. I'm not sure I would know exactly what all of them do. But I do know that our data scientists at work use them, and that's why they gave me that list. So I do know that they're very helpful. So one thing we are going to be using is the ADTK, or the Anomaly Detection Toolkit. This is an open source Python package for rule-based anomaly detection. For our anomaly detection example, this is what we're going to be using. It tends to be more for industrial IoT use cases, which is our bread and butter as far as customers go. We have a lot of industrial IoT customers. For us, we're going to be using the auto-regression anomaly detection, but as you can see from this list that I took from their website, they have many options. So you can choose which ones you would prefer to use for your own use case. TensorFlow. So I'm not going to be going over using TensorFlow. This QR code, as I said, there will be so many. This is one that you can go with if you want to know about using TensorFlow with InfluxDB. But basically, it's a machine learning and artificial intelligence platform. They use it mainly to build and train models, using mostly Python, but they do also have JavaScript. I haven't used it on the JavaScript side, just to clarify. If you haven't noticed, I mainly work in Python. That's why my track says it. Prophet. We are going to be using Prophet for forecasting. Again, I'm not going over that just because there's not enough time to go over everything. But basically, it works similar to like Holt Winters or triple exponential smoothing. It combines both seasonality, trends, and holidays. And again, resources for using Prophet with InfluxDB. You don't have to grab this QR code right now if you don't want, because there will be another where it has the full Jupyter notebooks, but just in case. Like I said, this is also just to make sure everybody's aware of all the tools that we're getting into, because there's a lot. What is Apache Parquet and Apache Arrow? So Apache Parquet is a data file format. It's designed specifically for efficient data storage and retrieval. The benefits is that it minimizes disk usage while storing tons and tons and tons of data. In the next slide, I'll show you guys what this actually looks like. It's got efficient retrieval and deserialization of large amounts of columnar data. And what is the difference between Apache Arrow and Apache Parquet? One of them is a runtime in-memory format, and Parquet data cannot be directly operated on, but instead needs to be decoded into large chunks. So InfluxDB is a database that is built with Apache Parquet. I'll have a slide here that kind of shows it, but basically, this is how we're storing your data. For comparison, when it comes to data stored in CSV files, this is a size comparison between that and data stored in the Apache Parquet format. You can clearly see that it's way smaller, way faster, way less data scanned, and just in general, a lot of cost savings. I'm going to be honest, I don't know where the cost is coming from this. I never asked, but we'll just assume it's Amazon S3 or something like that, considering that's what the size is. So that's what we're going to go with on the cost. And this slide's a little old, so it could be even more expensive. Who knows? So Apache Arrow is basically a framework for defining in-memory columnar data that every processing engine can use. It's language agnostic. The only standard is that it has to be a columnar memory store. So it's very good for running large analytical workloads on both modern CPU and GPU architectures. And specifically, it's got a wide range of programming languages, including C++, Java, Python, my favorite, and R. And I think it also nowadays has JavaScript as well, I thought, but I'll have to recheck on that one. So as you can see, this is basically how Apache Arrow formats the data when it's being called upon. It allows computational routines and executional engines to maximize their efficiency when scanning and iterating these giant, large chunks of data, basically. In particular, as I said before, it has to be a columnar layout, and it enables vectorization using single instruction multiple data operations included in most modern processors. And yes, I did just take all those words basically straight from the docs, as you can tell. It was not written by ChatGPT, I hope. It was written by a human who likes to use bigger words than I do. But obviously, this is really great for getting your data back in and out. You know, it's really funny how I swear these were formatted appropriately on my laptop, guys. I'm really sorry, but it's okay because I know what it says anyways. So one thing to note is that Apache Arrow also has Apache Arrow Flight SQL. And this is unshockingly specific for interacting with SQL databases that still makes use of that Arrow in-memory columnar format. So basically the difference here is that Aeroflight versus Aeroflight SQL is that one of them is more specific to query execution using SQL. So that's big. That's pretty much the biggest difference between these two. I'm going to go on to the next slide because it got a little bit less chunked out. So basically this one accepts a ticket that is implementation specific. It's got query language agnostic, which means it can work, for example, with something like we have InfluxQL, that's one of our querying language. I think Mongo's is called MongoQL or PromQL or something like that. That would be query language agnostic. It can work with either of those. The difference, of course, with the Flight SQL is that it is going to be SQL specific. But again, these are both implementation agnostic for the most part, where they can be used with, okay, well, the Flight SQL isn't as agnostic in the fact that you have to have a SQL query on your database. Like it can't just be a NoSQL like random language, but for the most part, they're agnostic in that they're not specific to any database engine. They're not InfluxDBs. They are a part of the open source ecosystem. So the big thing here is no serialization or deserialization cost. Since Arrow is sent directly between the database server and the client, that means you don't have to make any extra copies of your data. And specifically, this is solving this issue. You've got all of these different technologies, and you're just copying and converting between them because you're using them all in different ways, and you've got your data all over the place. It doesn't need to be that way with Arrow. And all of these, there's more than just this, by the way. These are just the only ones we could fit, like right now on the slide, and these are the ones that I'm the most familiar with. There is a wide range of technologies that support Arrow memory, so you can take advantage of this. These are just probably some of the more popular ones, to say the least. And anybody who's using Apache Parquet as their storage, you're good to go. That should work pretty much automatically. And like I said, there's tons of databases and storage engines that are using it. And this is another just example of how this looks. So InfluxDB, like I said before, we're built with Parquet, we're built with Apache Arrow, and we've got Data Fusion for our SQL engine. With that, we have our Flight SQL client libraries. So all those little logos down there at the bottom, those are all the client libraries that we personally provide to our customers that allows them to basically do RESTful interactions with the database. They can write their data in, query it back out. That's all being powered by Apache Arrow under the hood. And then we actually have a vanilla Apache Arrow Flight SQL one as well, but that's basically what's powering all those under the hood. And this allows us to connect with all of these other awesome technologies, because again, we're a database. That's all we are, that's all we do. So we don't do all the awesome stuff that all of these other great technologies do. And some of these we've already started to talk about. So to understand a few more performance differences when it comes to PyArrow in particular, this is the time in reading a CSV file with about 11 million records. When you compare it to Panda's CSV reader, which is their default engine, with PyArrow's, you can see that PyArrow is doing it about 15 times faster with Arrow's in-memory column restore, and it's even coming in smaller as well. So that's a great thing to see. It's great to see that it's working so well as well. So again, just a great example of how much more efficient it is to use. Another thing is that thanks to this, Apache Spark data frames to Pandas were once very much more inefficient of a process, and they had to go through basically serialization and deserialization. Now with the Arrow in-memory format, they don't have to do that anymore. Again, no more of that copying and converting, all that stuff that we talked about before, all that aggravating nonsense. This just does it straight away with PyArrow, and so you don't have to deal with all of that. So let's go into an Apache Arrow example. So this is pretty basic. Basically what we are doing here is we are creating a PyArrow table. It's pretty easy to understand this code, but basically we've got an array here that we've created from a list of values. It's basically just some animals, the amount of animals that we've acquired and the years that we've got them, which is all the same, it's all 2022. And then we go ahead and create that PyArrow table from those arrays. And we do name them animal count and year, and then we go ahead and we print it out on that side. So pretty straightforward, nothing super fancy or crazy going on here. This is us, so we'll go ahead and now build upon this. As you can see in this example, we're including our Python library called Flight SQL. This is specific to InfluxDB, but again, most people would have a Flight SQL client depending on the database engine that you're using, but most people would have something that looks roughly like this. And from this, we are querying. We're selecting all of our data from IOX machine data where the time is right now to an interval of about the past day. And then we're creating a reader to consume the results that we're receiving back. And we're reading all this data into a PyArrow table and just printing it out. So as you can see on the side there, you can see the PyArrow table is describing all of the headers basically of the table, where it's saying like the machine ID, the power. It's also describing the format that they are, whether they're like a string or a double or the timestamp. And then it's showing the actual values. Obviously, this is basically the full table result. Luckily, I was worried that this wouldn't look super great on the screen, but it looks like it expanded well. But this is the resulting data frame. We've included the 20 values within the head function just to make sure that it returns multiple time points for each sensors. So as you can see, we've got our humidity here, we've got a sensor ID, we've got temperature, and we've got a timestamp. This is without a doubt the most common type of data that I'm working with, that our customers are working with. This looks very familiar. And we have some Arrow utility functions. This one's highlighted in purple because we're going to take advantage of this one and we're going to convert it to a pandas data frame, which will make it basically more manipulatable for us. Personally, I almost always am just converting my stuff into pandas. You can also load the table from a Parquet file. So if you have a Parquet file that you have available to you, kind of like a CSV file, you can go ahead and read from it. And you can go ahead and save it to a Parquet file format as well. And you can do a little bit of aggregation. So here we're doing a group by the machine ID, and we're aggregating with the vibrations by the mean, the max, and the min. And again, converting it to pandas in the end. But the other thing that we like to do, so this is a really common thing that people need to do with time series data, which is called downsampling. So downsampling is, you've got a temperature data set, you've got a sensor that gives you data about roughly every millisecond or nanosecond. That's the common time frame for a sensor. But you really don't need it down to the nanosecond. You're just like a weatherman on the news, for example. You're not really showing people that much granular data. I'm being facetious, but this is true in most of our use cases. So what you want to do is you want to downsample. You want to say, give me the roughly, average or mean temperature for the past 30 minutes, 5 minutes, hour. That's cutting you out a lot of data points. And especially when it's done being monitored in real time. So like you're monitoring something, you're at a factory floor, you're paying attention to your devices on that floor and you're monitoring them real time. That's when you really care about that nanosecond timestamp. But once the day is done being monitored, you still need that data for historical reference. You need it for anomaly detection, you need it for analytics, but you don't need it down to the millisecond. That's when you start to downsample. That's when you start to say, like I said, give me the mean. This one, for example, is resampling by every 10 minutes on time. Give me the mean and drop everything that's not that. And go ahead and write that out for me. We're also resetting the index on this as well. So this is the table result comparison for us. So we come in with our larger data set, and now we've got a much smaller data set with a much more, obviously because it's being aggregated to every 10 minutes, the data is just a lot smaller. It's a lot easier to work with. And specifically what people tend to do with this is they tend to send that downsampled data back up to their database. Now, obviously, this could go onward to another DB. This is just a simple example because, again, this is all coming from a Jupyter Notebooks that us at Influx created. So just wanted to clarify on that. You could send it to many places, but basically most people, they'll downsample in something like Pandas, and then they'll push it back up. Or they'll send it onward to their analytics toolbox if they want to. And that's pretty straightforward. Again, this write is being done by our client libraries, which are just being built with Py. This is all PyArrow. So leveraging Pandas for analytics. So again, as I mentioned at the beginning, we're kind of going to be talking about joining because this is a big thing that people tend to do because time series data, it's so funny how many times people ask me if I am a replacement or if Influx is the replacement for their SQL database. And I have to explain to them that no, there's very few people who just have time series data. Most people have many types of data. Some of it's going to live in SQL, some of it's going to live in Influx. For example, I actually want to go back 1 second to look at this. Look at this data set here. This doesn't even have an ID on it, really. I mean, it has a sensor ID, I guess, but there's probably a lot more data going on here than what we see here. There's a lot more, there could be, where is this sensor living? Where's the, the industrial factory where it's coming from? All of that data is normally actually, funny enough, stored somewhere else. It's stored in a SQL database. Somewhere in the SQL database, there is a factory ID with factory names and a bunch of sensors that say where they live there. Because that's where it makes sense to store that data because unless the sensor becomes defective, it just lives in that spot. Like I said, SQL data is great for data that you're not really changing and manipulating a bunch. It's just staying there, staying stagnant and just chilling and waiting to be called upon, basically. So it's very common for people to join their SQL data and their data from a time series database. So that's why we're going to go over this. So we have our original data set up here. So this is really great for comparison. And basically, let's say we do a join and we give it no how parameter. So just an example really quick. That's what a how parameter looks like. It goes at the very end. When you don't give it a how parameter, it just will default to what's called the left. So when it defaults to the left, it means that it will grab all of, this is considered the left, this is considered the right, just to make sure everyone's aware. It will basically grab everything from the right or from the left. And when it finds something that doesn't match in the right, like as you can see down there, you can see courses right. It's got Spark, it's got Python, and then it's got 2 non-values. That's because on courses right, we had Spark and Python, but then we had Java and Go, and those are just gone. Be gone with them because they're not on the left, which makes it pretty obvious when we make it to the next slide. Now the nons start to switch the other direction, the null values, sorry. Null values start to switch the other direction. So we've got all of our courses on the right, and everything where there wasn't a value on the left becomes a null, and anything that didn't match at all, like for example on this one, Pandas is gone, and I do believe PySpark is gone as well. Those values are also be gone. Now we do an outer join. So with an outer join, we get everybody. Everyone gets combined together, and again, null values are added. So this is actually how I tend to combine my data quite a bit because I'm dealing with, normally I'm dealing with more inline data, like they match better, I guess you could say. I'm normally dealing with a data set that has IDs, like that value that I was telling you about before, the sensor IDs, and then I'm joining them in with my SQL data. And then you have your inner joins. So with your inner joins, if they don't match up, your course is on your left and your course is on your right, data be gone. It's only going to show you the 2 that actually match, and that's what's going to stay. And then if you join on a column or an index level, if multiple values are given, the other data frame must have a multi-index as well, by the way. It can pass the array as the join key, and basically from this one, now you only got your Spark and your Python, and you have lost your, and this one actually, it works pretty well because everybody here has the fee, the duration, and the discount. So you've got all of those right there. And then in this one, you still get your R1 and your R3. So this is the big difference between these two. So basically in this one, you've got your first one here. It adds them all in, but it still calls it courses left and courses right. In this one, it just becomes courses and it drops the index. And in this one, it keeps the courses, again, drops the left and the right, but also still adds the index as well. Sorry, those 3 kind of get a little confusing. And then we can also do a pandas rename column. So this is also very common when you're dealing with data. For this one, it's pretty straightforward. We're literally just renaming tests to be all capitals. But obviously, you could see this being a little more helpful if you're dealing with a data set where, you originally had courses left and courses right, and now you want to go ahead and change that name to be a little bit less weird. There we go. Another one that people tend to need to use is the reset index. That's basically just adding a new index column and changing the old index. So if we add the drop, the column will not be included as well. That's if the drop true is on. So let's go into some examples here. So an autocorrelation example will be first. So what is autocorrelation? I feel like most people in this room probably already know what this is, but basically it's referring to the degree of similarity between a given time series and a lagged version of itself over successive time intervals. In other words, it's basically intended to measure the relationship between variables' present values and any past values. Basically, is there a correlation to the data over time? As you can see, this would be what a positive correlation would look like versus a negative correlation where the values seem very much random and not related. So in our example, and I'll have QR codes at the end of this as well, we're pulling in from the National Oceanic and Atmospheric Administration Center, NOAA otherwise known as, and we're specifically looking at water levels and temperatures for a river in Santa Monica. So we're going to be using the InfluxDB Python client library, which again is powered by Apache Arrow, and a Jupyter Notebook, which will be linked at the end. So once we get all that data into Influx, we go ahead and query it. And this is the query that we're doing. So we're saying client query, select the mean of degree as H2O temp from this database, and we also want we want to group it by the time of 12 hours, the past 12 hours, and limit it to 60 so we don't end up with tons and tons of data points. And the rest of this is pretty much just getting it. We're just getting the points here, we're getting into a pandas data frame, and then we're just setting up the X and Y plot, which will look roughly like this. So from looking at the plot, it's not currently really apparent whether or not our data will have any autocorrelation. I can't detect any presence of like seasonality, which would yield to a higher autocorrelation. So now we're going to go ahead and actually calculate that autocorrelation with the pandas autocorrelation method, which is coming from the Pearson correlation between the series and its shift itself. And basically the way that this one works is that if the values are very close to 0, it indicates that there is little to no correlation between them. And normally the value is between -1 and 1, where 0 is, no linear correlation. Above 0 would be a positive correlation, and below is a negative correlation. And so as you can see here, we're pretty close to 0. That's probably our closest. So we're pretty much not getting any autocorrelation here. However, with the autocorrelation plot, we can see that the values for the ACF are within 95% confidence interval, represented by this solid gray line, which verifies that our data doesn't have any autocorrelation. It's basically just saying, to be a little bit more in English, I suppose you could say, I originally assumed that the water temperature would be, it would have more autocorrelation to the time, basically. But that's not always the case. Certain streams and rivers are actually the same temperature year-round. They don't tend to change too much, and this happens to be one of them. But the ACF can also be used to uncover and verify seasonality in time series data. So we're going to look at water levels from the same data set. Now this time we're going to go and do a much longer time value on this. So again, we're still looking for our location to be Santa Monica, but this time our time is going to be for a few days basically. And let's go, again, this is just the query. This stuff is all pretty much exactly the same. It's just, again, creating it into the data frame and graphing it. So just by plotting the data, it's fairly obvious that there is a little bit of seasonality probably existing, evident by the predictable pattern in the data, but we can still verify this assumption by plotting the ACF. So from the ACF plot above, we can see that our seasonal period consists of roughly 246 time steps, while it was easily apparent from plotting the time series in figure 3 that the water level data has seasonality. That isn't always the case. But yeah, so with this, we're just using the plot ACF to get this. And I'm going to link in a QR code this one, but basically this is a blog by the author Seen Abu, who shows how he must add a seasonal component to his ARIMA method in order to account for seasonality in his data set. It's a great example of how using the ACF can help uncover hidden trends in your data. And that would be those QR codes. So this is the Jupyter Notebook with a few more autocorrelation examples. This is a blog that kind of goes over and explains this further. How to use time series for forecasting pitfalls and seasonal ARIMA with Python. I'm still going to have another slide later on with more QR codes, but this is just for this one in particular. So anomaly detection and forecasting. Again, this QR code will show up again, but in case you want more context around it, this is basically some of the examples of anomaly detection. And whether you're dealing with a single time series or multiple time series, the ones that would be more appropriate for your use case, and then some examples of forecasting. And both of these live inside of the GitHub project with Jupyter Notebook examples inside that QR code. Like I said, there's a lot to go over here, so I can't go over exactly all of it. So we're going to be using, as I mentioned before, from the ADTK toolkit, which is an open source Python library for anomaly detection. We're using the autoregression AD, which will detect anomalous changes from autoregressive behavior in time series. It can capture the autoregressive relationship, the relationship between a data point and points in the near past, and can be used for cyclic but not seasonal series. So after we have acquired our data in a pandas format, this is a pretty simple data set to say the least. We've got a timestamp, a value, and a label of 0. We can prepare the data for consumption, which basically just means that we're creating the index, we're dropping the label column, We're converting the timestamp column to a pandas datetime object, and we're setting the timestamp column as the index. So those are the three things that we're doing here to get it ready, basically. This is also a great example of when you're just working in general with a CSV and pandas. So visualization before we're actually putting in that algorithm. And this is using that AD function. So this is pretty straightforward. We're basically just, these are just the two import values basically. And then we're using this auto regression AD. And again, this does have plenty of documentation around it. And obviously, as you can see here, it's got a lot of different options when you actually start to set it up. And this is what it will actually look like when you're graphing it. So this is that auto regression. You can see from the little red data points, you can see where there are anomalies detected in our data set, which isn't too shocking because the data set was pretty basic. And we purposely added those spikes up and down. So this is the full resources page. So as I said before, most of these I've already mentioned. The PyArrow docs are right there in the center. That's one of the ones I didn't actually mention earlier. I just wanted to make sure it was a part of this. And I think everything else here is all, like I said, this has all been shown before, but I've been asked many times to have more QR codes, more resources basically for people. Another one is to try it yourself. So all of these projects are in the one on the right in our Influx community. That's where we add, beyond data science projects, that's also where we add just other projects that we've been working on in all kinds of time series use cases. And then this is just our website. And yeah, that is the end of my slide deck.